Hello, my name is Jonathan Bisnet, and in this video I'm going to talk about a situation I kind of ran into as I was developing with a friend, my lab partner, on an Edison based project. We actually had a situation where we were attempting to rebuild a robotic well, it was a student trainer, but it's kind of done up as a robot with a Zilog EZ8 microcontroller as its central processing unit. And the way this thing worked is it actually included a board of education board for the student to, in essence, wire up some things. So it brought a number of ports out from the microcontroller to a header alongside a very small breadboard that also had on an adjoining side power and ground. And what the student would do is put together small circuits. As an example, they might have to put 3 LEDs on there with resistors tied to specific ports, and then using software in the microcontroller turn those on and off in some pattern or form. Additionally, they might have had a project that would require them, as an example, to use one of those ports and tie it to a switch, a normally open switch that had a pull-up resistor on it. And when you press the switch, it connects the port to ground, and use that as an input for the microcontroller. Or, potentially any of a number of other devices. Could be small motors or transformers or relays or whatever. So the situation I kind of ran into is if I put the Edison into this device, the Edison has a 1.8 volt, 1.8 volts on its ports. It's not 5 volt tolerant. 1.8 volts is not going to do much to drive, as an example, a blue LED, or potentially even a green one maybe. So the situation I was looking at is, how do I get 5 volts out there for each of the ports for the circuit without knowing whether that port's going to be input, output, or both? I can't really do the level shifting, which is done in a lot of my other blog entries and things like that, showing pull-up resistors, because at that point, without knowing what's in there, if I use a pull-up resistor, the resistance itself could have an impact on the device in place. As an example, a lot of the circuits I used for level shifting for the Edison from 1.8 volts to 5 volts had a 10k ohm resistor in there. Well, put that in there and tie the lead to it and you got a small issue. So I had to come up with another way, and what this video shows is kind of what I came up with. I went through a few iterations of things. I started playing with a couple of different circuits and nothing really seemed to be working, and my lab partner jokingly threw out the idea, well, why don't you just use an op-amp? And we started playing with that, looking at different circuits, and I couldn't really get it to come together the way I wanted, but there were some points of promise in it. So as I played with it a little more, it suddenly dawned on us that maybe a comparator would work better for the purposes of level shifting. So I took the concept of the comparators and played with it, and ended up with a circuit that had 2 comparators in it, back-to-back. In this case LM311s, and which actually worked out very well for me because they're an open emitter, open collector configuration. So it truly does isolate the impact that the comparator has on another circuit from the circuit that's testing for a various level. I don't know if I said that very well, but that's kind of what I'm trying to get to. So in the schematic here, you'll see I've got 2 comparators, what I would refer to as an upper and a lower comparator based on the way they're laid out in this circuit. And they are both powered by 5 volts, single supply rail. They're LM311 P's, single supply rail. And what I then do is, depending on which comparator it is, I use a very simple voltage divider, two 10K ohm resistors, to kind of set the midpoint for the appropriate voltage to the appropriate input. Because this is coming off the Edison, it's digital logic. So for the most part, something's either on or off. So it's either 1.8 volts or 0 volts. And in theory, since it's going to the Edison and we're not attempting to do anything analog based, the input's 5 volts. And at that point, you're dealing with either 5 volts or ground. So again, two 10K resistors will set the midpoint at 2.5 volts. So digital logic works fine for that purpose. What I then did was take, and the upper one, as an example, handles the initial input. Let's first look at this. Down in the bottom right hand corner, you'll see two partial circuits. There's one that's marked LED output that has a LED along with a 1K resistor to ground. And then there's another one that has a 10K ohm resistor on the switch, tying the switch input to 5 volts. And the switch itself is a single throw, single pole, single throw type, normally open contact. And what I did is, for the first circuit, I took the assumption of a LED. They want to flash a LED on their project. So I took, as you can see, also on the upper right, there is a breadboard pin and an MCU pin. The MCU pin is the connection to one of the pins on the Edison. The breadboard pin is a connection to one of the circuits. In this case, I had the LED output or the switch input. So this allows me to test it using either or. So if you take the Edison, let's assume we want to flash a LED, and we tie the Edison to the MCU pin, you'll see it basically puts that voltage to the inverting input of the upper LM311. The non-inverting input is tied to 1.8 volts and ground, so the non-inverting input's at 0.9 volts. So if the Edison outputs, as an example, 1.8 volts, then the non-inverting input will be higher, and that will in essence turn on the transistor that's part of that LM311. And when it does that, it will connect the gate of Q1, which is a MOSFET, a P-channel MOSFET, in this case a high side switch. It will connect it to ground, which will turn on that MOSFET. And at that point, the breadboard pin will have 5 volts present, which, if it's then tied to the LED, will light the LED while it's a 1. By the same token, to follow the rest of the path through, when that's a 1, when the breadboard pin is at a 1, you'll see that also feeds the non-inverting input of the lower LM311, and its inverting input is tied across 5 volts with a voltage divider, so anything over 2.5 volts at that point is going to be seen as a high, or a 1, which would, in this case, because it's higher, it would turn off the transistor that's located, that's part of the LM311. And with that transistor off, what the output is pulled up by that 10K ohm resistor, as well as whatever's on the MCU pin. So in essence, you're seeing a 1 right where you had it initially on the non-inverting, on the inverting input of the upper LM311. So it works full circle. If I output a 0 to this piece, you will then, from the Edison, you in essence are taking the inverting input of the upper LM311 to ground, which would take it below the non-inverting input, which in this case would turn off the transistor on the output of U1. When it is off, there's a 10K pull-up to 5 volts that's pulling the gate high on the Q1 MOSFET, which will turn it off in this case, so the breadboard pin will not be seeing positive voltage. By that same token, then, that the lack of that voltage will appear on the non-inverting input of the lower op-amp, lower comparator, which is looking for something over 2.5 volts as the midpoint. Because the inverting input is higher in this case, the 2.5 volts, it will turn on the transistor on the output of U2, which will basically connect the MCU pin to ground through a small 1K ohm resistor, and that resistor is in there basically to do to prevent some issues between slightly differing voltages should they occur, so things don't fight each other. But anyway, the MCU pin at that point sees ground, so it sees ground, as well as the fact that you're also seeing ground at the inverting input of the upper LM311. So it carries all the way back through. So that's how that works. And if you look at the circuit here that I've got built, I've currently got it set up, and I'll try to give you some close-ups of some of the stuff, although it's a lot harder to see on the breadboard. See, it doesn't focus well. It's a lot harder to see on the breadboard than in the schematic. But I've got my two LM311s, and there is my my MOSFET, my P-channel MOSFET, and that the output of that, the drain is connected to, yes, the drain is connected to the lead, and you can see from there it's connected to ground through a resistor. So that piece is working, and the input from the microcontroller is coming in here, oops, right here, to this this white wire right here. This other one is what's connected over to the other LM311P. But anyway, so at this point the Edison is turning it on and off it's on like a 50% duty cycle, and it's simply raising and lowering the pins. So this part works great. So let me pin it, and then I'll talk about how to use it as an input. Alright, I'm back. Now, if we look at this the other way, in this case I'm going to hook the breadboard pin to where it says switch input. And the way we kind of look through this is, when that switch is in its open case like it is on the diagram, you've got a 10K pull up to 5 volts. So the breadboard pin sees 5 volts, which travels to its non-inverting input on the lower LM311P. So you have 5 volts there compared to the 2.5 on the inverting input, which in essence turns that turns the transistor on U2 off, so that at that point the MCU pin does not see positive voltage. In essence, it sees it does see 5 volts because of the pull-up resistor R7 that ties it to VDD. So it's seeing it's seeing 1.8 volts because of that pull-up resistor, which is in essence the same thing you're seeing off the switch because it's pulled up to 5 volts. So the Edison sees 1.8 volts. That's also what's fed into the inverting input of the upper comparator, which is comparing that against 0.9 volts. So the inverting input on the upper comparator, the inverting input is higher, therefore the transistor on the output of U1 is on, which pulls the gate on Q1 to ground. When it's pulled to ground, that turns on Q1, so at that point 5 volts is fed to the breadboard pin. So coming roundabout, you're getting 5 volts right back at the switch. Even though you had a pull-up resistor there, you're getting 5 volts there. Now, if you press the key or the button, you'll see that at that point, the breadboard pin sees a ground signal, and that is fed into the non-inverting input. And when compared to the inverting input's lower, so the inverting input wins out, that turns on the transistor on the output of U2, which pulls the MCU pin to ground. And it also basically pulls the inverting input of the upper LM311P to ground, which takes it below the 1.8 volts that's on the inverting input. So that wins out because the non-inverting input, because that is higher. The output transistor of U1 is off, and that means that the gate of Q1 is pulled up to 5 volts and is therefore off, and the breadboard pin is not getting any voltage, is not getting the 5 volts. It's basically seeing the ground signal that's coming from the closed key. So again, it goes full circle and works just fine there. So what I did in this circuit, if we look at the setup here, is I pulled the pin out that was driving I pulled the output out that was driving the LED and connected it over here with the resistor to 5 volts to the switch, to the button in this case. And what I did down here is I put together a small little level shifting circuit so that the output, the 1.8 volt output that's coming in on this wire from the Edison, will basically turn on and off this this NPN transistor. In this case, it's 4401. It will turn the base. It'll apply current to the base or remove current, which will turn the LED on and off. That's tied in this case to 5 volts. So I can use 1.8 volts to drive a 5 volt LED without risking damage to the Edison. So what you'll see is when I press, let me make sure we're zoomed out far enough here. When I press the button, the software that's running will cause the LED to start blinking. You kind of see an interesting flicker in there because of the camera versus what's going on with the LED. But then when I press it again, it'll stop. So I've basically written some simple code that on each press of the button, it flips back and forth between flashing and not flashing the LED. So, relatively simple circuit. Anyway, I don't know that you necessarily have a reason or a use for this specific type of circuit. I did want to present it, and I will, in the information below the video, point you to my blog where I go into a little bit more detail about this and give you a better view of the schematic, etc. This is not something I would generally use if I were simply interfacing certain components to the Edison. I've got plenty of other posts in my blog that talk about the different situations. This is more a situation where I had to use each pin in a manner in which it could be either input or output. It could have differing voltages that drive it, and of course the Edison is at 1.8 volts. The other twist that was thrown into this is that in rebuilding this and making it work like the Zilog did, the switch needed to be a high side switch, so it required a P channel, and I did use a MOSFET in this case because of the very low RDS on, which wouldn't have a material impact on any circuit that was built off of it. So that's how I did this. I hope you found it interesting. I do plan on doing a few more videos here and there related to using the Edison with various devices, and if you're interested in the Edison, I would encourage you to watch them. Thanks for watching. Goodbye.